Hello everyone, in this video we will look at how to build a model using TensorFlow. So for this video we will use iris dataset which is available within TensorFlow library. So this dataset contains various species of plants which we'll have to classify. So first we will load the iris dataset, okay, and we will look at the keys. It has data and target and other keys. So let us convert the data iris.data into a data frame, and we'll provide the feature names as the columns. Okay, so if we look at the first few records, we can see that various features available are the sepal length, sepal width, petal length and petal width. So these are the features available. So let us look at the target column. So if you look at iris.target and convert it into a data frame, so we can see the first few rows over here. So let us look at the count of this iris type. So we can see there are three types, 0, 1, 2, each having 50 each. So there are 150 rows in total. So let us look at the target names. So if we look at the target names, we can see there are three types: Setosa, versicolor and virginica. So these are the plant types which we'll have to classify in our as part of our model building. So to start with, let us split the data. The usual routine, we'll split the data into train and test. Okay, we'll use a scikit-learn train test split to basically split the data. So we'll use 90% of the data for training and 10% of data for testing. Okay, so once we get xtrain and xtest, one thing to note here is the target names is categorical in nature, so we have to convert it into numerical format. So one of the ways to do it is to use one hot encoder, which will convert the categorical data into a form of a binary format. Okay, so we can use keras utils dot to categorical to convert it. So yeah, so that will convert the white train and white test both into one hot encoder format. Now let's look at the xtrain, the shape of the training data. Okay, so there are four. It's a 4 comma, which means since we have 4 features, it has it has 4 columns. Okay, so this is important because this xtrain will be passed as input to our neural network. So in knowing the shape is very important, as we'll see sooner. Now let's try to build the model. So, or in other words, build a neural network. We will use sequential tf.keras.sequential. So a point to note about sequential model is that it stacks the layers linearly. Okay, so and we will use dense layers. So dense is mainly densely connected neural network layer. So densely connected means each neuron is connected to every other neuron in the layer, in the next layer. So it basically implements this operation. If you see, output is activation function dot product of input and a kernel, and we're adding a bias. So this is the implementation of dense layer. So when we build a neural network in the sequential format, using sequential API, so we can stack the layers. So first layer, I'm using a dense layer with 32 neurons. So first argument is number of neurons, and we'll use ReLU activation function as a nonlinear activation function. Here in the first layer, we should give the input shape. So the input shape we know it has 4 columns, so you'll use a xtrain dot shape. So that way we are telling our neural network that the first layer has a shape of, if you see, if the shape here, it has a shape of the 4 columns. Okay, so we'll stack 2 more layers. These are 2 more hidden layers, so each having 32 neurons each. And finally we have the output layer. The output layer, we're using softmax as the activation function because we are using a multi-class classification. Similarly, since we are using a multi-class classification and we have 3 output classes, so we'll use 3 neurons in the output layer. Okay, so this is how we build the network. So once we have built the network, The next step is to compile the model. So a few things here. We will have to use one optimizer, and we have to we provide a loss function. So the loss function will use categorical cross entropy. So what is categorical cross entropy? It computes the cross entropy loss between labels and predictions. Okay, so entropy is a measure of uncertainty, and hence it is related to probability. So there are two variations of cross entropy. Binary cross entropy we'll use for binary classification, and we'll use categorical cross entropy for multi-class classification, where we have used one hot encoding. In our case, since we use multi-class classification, we'll use categorical cross entropy. Now coming to optimizers, so these are optimization functions. Neural network, as you know, is all about optimizing the loss function. So there are various optimizers available like ADAM, we have RMS prop or stochastic gradient descent, SGD. So currently we are using ADAM as the optimizer. Similarly, for metrics, we can use various metrics. We can use accuracy as a metric. We can use a mean squared error or F1 score and so on, depending on the problem statement. Here, we'll be using categorical accuracy as our metric. So there are two ways to provide the optimizer. If you see, we can use in the first format, we can just mention the optimizer in the single quote, ADAM. In the second format, we are actually initializing the ADAM class, and we are providing that as an object. The advantage with the second option is that we can, if we have to customize few arguments, we can do that. For example, here we wanted to give learning rate. So learning rate is the rate at which the network learns the weights. Okay, how much, what kind of steps it takes. So generally it's a number between 0 and 1. So we are using the value 0.01. So a smaller learning rate means it takes smaller steps to learn, and a larger learning rate means it takes larger steps to learn and to reach the optimal state. So we'll use a learning rate of 0.01. So this is generally a hyperparameter which has to be learned via experimentation. Okay, so basically this is how we compile the model. So we're using model.compile. So once we have compiled the model, the next step is to train the model. So far we have not used the data anywhere. Now we use the input data to train the model. Now there are a few concepts like epoch and batch size. Epoch is one complete pass of all the training samples through our network, which includes backward and forward pass. Okay, and batch size is the number of training samples in one pass. So as you can see, if I use all the training data as the batch size as the entire training size of training data, the whole data has to be in memory. So imagine if we have image data and we have 1,000,000 images. If you use a batch size as 1 lakh or 1 million, the same as a training data set, the whole 1,000,000 images will blow into memory. So we may not have sufficient memory. That is why generally batch size we use a smaller chunk of the entire training data. Now, if we use a smaller batch size, what is the number of iterations? It is generally the number of passes required, wherein each pass we pass the batch size of examples. Let me give an example. Suppose we have 1,000 training samples and batch size is 50. Then we need 1,000 by 50, which is 20 iterations to complete one epoch. So one epoch is, remember, one complete pass of all the training samples. So okay, with this information background, let's do model.fit. We pass the training set, the white train, and we also specify the validation split. So this is optional. So what happens here is, remember, we have split our data into train and test, but we can also do a k-fold cross validation, right? So for that we can use a validation split where we have given 70-30 approach, 70% training data, 30% validation from within the training samples. So it will do a cross validation. So here we have specified 50 as a batch size, and let's try with 100 epochs. So let's see what happens. So basically if you run this, it will start training, and all the epochs if you see are printed. In each epoch we can see the loss, the categorical accuracy. It also shows the validation categorical accuracy, which is the accuracy in the validation set. So okay, all the 100 epochs have been completed, and we can see that the final accuracy is 0.95. Okay, so if you see here, we have seen higher accuracies in between. So but it, since we have given 100 epochs, it completed all the 100 epochs. Okay, and accuracy, the final accuracy in the last epoch is 95%. We will look at in next video how to experiment with this, but for now let us look at the prediction. Okay, we'll use the same model. Now its model is trained, use model.predict, pass the test data set, and find out what happens with the ypred. Let's print out the ypred. So we'll get the different values. To make sense out of this ypred, we can find out the TF Keras matrix categorical accuracy. So we can pass, so here a 1 means that the test and the prediction matches, 0 means it doesn't match. So in our case, we can see that everything has, in the test set at least, everything has matched. So we have actually a near to perfect model, but we have, yeah, so there is no zeros here, which means the all the cases y test and ypred, they have matched. So we can also print out the y test, the values of the y test and the ypred, so we can compare them. So we can see that we have already one hot encoded, so we can see that the values, the match, the y test and the ypred values the match. So we have a near perfect model. So this is pretty much how we build a model in TensorFlow, how we build a network, how we compile it, what is an epoch, and that's it for this video. Thank you for watching.